Welcome to The Explainer. Today, we're taking a look at advanced prosthetics, but we're framing this specifically for the InfoEngineer. We aren't just going to look at these limbs as mechanical marvels, we are treating this as the ultimate data processing and human-machine integration challenge. Because as we'll see, the real marvel isn't just the robotic hand itself, it's the invisible flow of data connecting mind and machine. We've got a lot of ground to cover today. We'll start with the human-machine translator, then tackle signal fidelity and noise, look at the sensory feedback gap, explore this crazy concept of twin tach for sight and touch, and finally dive into the augmentation frontier. Let's get right into it. Section 1. The human-machine translator. So what is the absolute hardest part of building a bionic arm? Honestly, most people look at a modern prosthetic, with its 20-plus degrees of freedom acting like a small, independent computer, and they assume the physical hardware is the main roadblock. They think the motors, the joints, the physical mechanics must be the hardest part, but actually, that physical construction is largely a solved problem. It is definitely not the hardware. The real frontier here is the translator. See, our brains don't send neat, perfectly packaged lines of code like move arm forward or close hand. Nope, they sent complex, chaotic bursts of electrical energy. The true engineering challenge is building a decoding algorithm that can actually learn what a messy, highly specific pattern of brain electricity means when a user simply thinks, pick up this cup. To build that translator, engineers lean heavily on tools like electromyography, or EMG. Basically, by measuring the electrical activity naturally produced by the muscles, say in a residual forearm, we capture this raw biological data. It's the vital bridge that gives our algorithms the physiological input they need to actually decipher human intent. And that sets up this incredibly strict four-step engineering pipeline. It's an absolute must for creating prostheses that feel like a true part of the human experience. You have to obtain the signal, accurately decode it, output it to the physical device, and finally, provide feedback back to the user. If you miss even one of these steps, the entire illusion of embodiment just completely breaks down. Which brings us to Section 2, signal fidelity and noise. When we look at more advanced brain-computer interfaces, the signals are originating straight from the motor cortex. That's a part of your brain handling the planning and execution of voluntary movements. But trying to read those signals, it is literally like trying to listen to a whisper in the middle of a heavy metal concert. The biological environment in there is just incredibly chaotic. To handle that chaos, modern BCIs use a very specific three-step signal processing pipeline to tackle the massive signal-to-noise ratio. Engineers have to relentlessly apply noise removal, extract the relevant features from the data, and then classify them to figure out what the user actually wants to do. If we don't use sophisticated machine learning to filter out all that biological background noise, we're talking heartbeats, stray muscle twitches, even interference from power lines, the final classification is just going to fail. And as engineering professionals, we have to treat this as critical infrastructure. If an algorithm crashes or misreads a signal, a user can't just reboot their arm while holding a pot of boiling water, right? Modern systems require intense redundancy protocols and safety measures that instantly lock the limb safely in place if that neural signal ever drops. Moving on to Section 3, the sensory feedback gap. Okay, picture this. A user can command their bionic arm to grab a warm cup of espresso. Amazing, right? But without bidirectional control, they have absolutely no idea how hard they're squeezing. They could crush the ceramic to dust or just drop it entirely. And worse, they wouldn't even know if the cup was burning hot. This is where haptic feedback comes in, and it is the real frontier right now. It closes the control loop by sending critical physical data, like vibration, pressure, and temperature, straight back into the user's nervous system. We are transforming what is essentially a one-way remote control into a true two-way biological extension. When you map out this bidirectional control, you get a dense matrix of sensors right in the prosthetic fingertips. They detect force, temperature, contact points, and then all that physical data gets translated back into electrical stimulation. That could be through physical tactors vibrating against the skin on the socket, or via direct neural implants, tricking the brain into perceiving it as actual natural touch. Section 4. Twin tech, sight and touch. For decades, artificial vision and bionic touch were developed in complete isolation from one another. But researchers recently broke through a massive clinical wall. They proved that visual cortical prostheses and somatosensory cortical prostheses actually use functionally identical BCI architectures. I mean, the hardware, the algorithms, the microstimulation patterns, they are exactly the same. Researcher Giacomo Valli really hit the nail on the head here, noting that these fields have had parallel development but basically never talked to each other. Merging them creates this incredible cross-pollination pipeline. A mathematical breakthrough in generating visual flashes for blind patients can now instantly optimize how we map texture motion in a bionic hand.
The fundamental biological logic behind this is just mind-blowing. Brain cells don't see light, they don't feel pressure. They only speak one language, and that's electricity. Whether it's photons hitting your retina or a fingertip pressing against a table, your sensory organs are just converting physical events into electrical frequencies. So theoretically, one unified technology can restore any lost sense just by plugging into a different lobe of the brain.
And finally, Section 5, the augmentation frontier. It all starts with neural plasticity. Because our brains are so wonderfully adaptable, they can reorganize their own neural connections over time. Users adapt to the point where they literally forget they're operating a machine. The bionic limb, or that artificial visual feed, becomes fully embodied. The brain just accepts it as a natural part of the self. We are standing on the edge of a massive paradigm shift. This tech is rapidly pushing past clinical restoration, which is just helping someone walk or hold a cup again. We are entering the frontier of true human augmentation. We're talking about enhancing sensory and motor functions well beyond natural biological limits. So I'll leave you with this provocative thought. If a sensor matrix in a bionic finger can process heat or pressure faster and more accurately than a human nerve, where exactly do we draw the line between repairing our biology and completely upgrading it? Thanks for joining me on this explainer, and keep questioning the invisible challenges around us.